As a true professor, I brought props with, so I'm very excited to be here. Thank you for the nice introduction and invite to be here. Always excited to talk about the Visible Heart Lab, and kind of uniquely, I was asked to fit it in the work I do on hibernating black bears, which I've been doing for over 25 years. And actually, right before this, I actually loaded all my equipment from the lab to be able to go to a bear den here in a week. And it was snowing out, which is bad news for you guys, but good news for me because I want the bears to stay put. All right, so kind of what I'm going to do today is I'm going to just really discuss our translational research, and that's a big focus of the Institute for Engineering Medicine, is that you can do work, but you want to try to bring it to clinical practice. I'm going to try to show you how the work we do on hibernating black bears, we try to make translational. We do that routinely. I did it yesterday in the lab. And then really, talk about therapies. We're trying to work with cardiac surgery to bring hibernation factors into cardiac surgery. So I run a large research lab. I have one of the coolest jobs on the planet, by the way. And I have a large science research staff, full-time programmer, lab coordinator. Right now there's 8 PhD students, 3 master's students, 2 postdocs, and I've trained several hundred graduate students. And we've had this huge partnership with Medtronic for this over the years. And that's the Visible Heart Project, and that's been for over 27 years. And uniquely, what we'll do is a lot of different projects that all kind of fit together. And so the lab has grown over the years. So we'll do target drug delivery work, which we did yesterday. We did a high-dose omega-3 fatty acids in the pericardial space before we recovered the heart for reanimation. And that's work that we hope will get into the surgical space soon. But we use it. We've been using it for years because it's hugely successful. Like I said, we go to bear dens. I'll show you some of that work as well. I've got some slides and hopefully some videos will play for you. We do muscle force assessment in patients with neuromuscular disorders. We still have ongoing clinical trials with collaborators in Switzerland and the University of Minnesota. Do a lot of work on organ transplantation research. And that's heart, lungs, kidneys, other organs. And we actually have a National Science Foundation Engineering Research Center, which the University of Minnesota is part of, on organ preservation and tissue preservation. So maybe preserving valves where you could actually have them grow for the congenital patient. Big thing we do, though, is outreach education. And, was just at a STEM event with several hundred kids a couple weeks ago. We have hundreds, or I should say thousands of visitors to our lab during a given year. We bring in high school students, university people. We've had patient groups come. So it's, a big, important mission there. And we do, also tissue work, like I said, clinical trials, but the centerpiece still is the Visible Heart Project. And there's a picture of Ping Yang, one of the scientists I've worked with for 20 years, and Jeff Martha, the CEO of Medtronic. And he was doing an implant of a leadless pacemaker in a reanimated heart. So this is the setup. So, we have state-of-the-art equipment. Everything has to be assembled and disassembled. We did this yesterday, and this case is a video from a reanimated human heart that we did. And so it's really state-of-the-art imaging equipment, so we can actually better understand what imaging you would do during a given cardiac procedure, train individuals to do that. We have people from around the world coming to our lab to visit, and we do live webcasts out of the lab as well. And so we are using, uniquely endoscopes, but we'll use IVUS. We do, optical coherence tomography. We just got a brand new 40 echo system yesterday, and then high-speed cameras. So what we'll do is we'll take the heart, and typically we're using animal hearts. So this is the method I use to remove the hearts. I studied this film, and I really have strong hands, so don't get me mad. And you know, I've been showing this for years, and I thought, wait a minute, this is getting old. But Indiana Jones 5 just came out, you know, so it's still relevant. And I don't do this methods, but I do wear the headdress in the lab when we do the heart isolations. No, I don't have the headdress with. It's really big and heavy. You know, we've had an amazing privilege to reanimate human hearts. We've done 95 of these. The last one was a month ago. That means there's an organ donor. The heart's not deemed viable for transplant. We can get it to the lab within 4 to 6 hours like a transplant window. It has to be intact. We have to have a whole team there to do it, so it's rare. We'll do 3 or 4 of these a year. And this is an amazing gift for research. And LifeSource, the local organ procurement agency here in the Midwest, helps us get these organs. For the first 5 years, I went and recovered them myself, but now the residents and fellows will do that, and they'll bring them to the University Hospital. And then for the first 2 hours after it's reanimated, we dedicate to collect educational imaging. And that means we're looking at all the functional anatomy, and then that goes on the free access website. Then after that, the grad students that are doing work on swine hearts can do it on a human heart, making their work translational. And then after that, we collaborate with Medtronic, and they can put various devices in there for physician training, patient education, and again, but that has to be publishable information. So like in this case, this was a transcatheter aortic valve replacement, or a TAVR, that we did it back in 2010, before this was even FDA approved. So we do a lot of the early preclinical testing of the Medtronic devices, and this is a transcatheter device, which means they put it up through your femoral artery, typically. They bring in the tool, and this is one like for the pacemaker. This is a leadless pacemaker tool, and it can steer, and then you deliver the device out of it. And so some patients have open heart surgeries. They'll need pacing. They'll usually put a lead in, but now they can go to leadless pacing systems, which are much easier to use. And actually, the batteries on these Medtronic Micra 2 last for 16 years. So you can kind of see the whole thing. Uniquely here, we have clear perfusate. There's no blood, so we can see everything. That means the heart will stay viable for some 5 to 7 hours, but the trade-off is we can see everything, and we can use the multimodal imaging. And then you're seeing the valve deployment there. That little hole is the coronary ostia, and one of the worries with a lot of these is that you might occlude it or block it. And so that's a lot of our ongoing research in the lab is on post-TAVR PCI or coronary protection during a transcatheter procedure. And a lot of work now, people are living longer with their aortic valve replacements. So if you get a tissue valve replacement, often they'll do a TAV in SAV or a transcatheter valve in a surgical valve. And so we're studying that as well, and studying the interactions in the lab. And all these images are on the website. So this is the website there. It's the Atlas of Human Cardiac Anatomy. There's over 5,000 videos and still images on there, and we add to it all the time, and it's open to everybody. This is one of the PhD students, Michael Balecki's work. Michael just got back from Tokyo Valves this week, where he presented some of this work. And this is where we're looking at transcatheter valve and transcatheter valve. We're looking at post-transcatheter valve PCI. So if you have a coronary problem, can you get back through that valve and deploy something? And or if you're worried about a low-placed ostia, should you protect it ahead of time? And so you can do different procedures with it. This is what the valve frame looks like. It's a really cool nitinol material that basically you heat it under temperature and it gets this shape. Then it's porcine pericardial leaflets that are laser cut and sewn in. And then this is put in the catheter. And then in the warm body, deploy it and goes to this predetermined shape. So what we'll do in the lab, we have our own micro CT scanner. So after we do a procedure, we can scan that heart, get down to a 15 micron resolution, and then 3D print it. So we have collaborations with North Star Instruments, which is up in Rogers, Minnesota. They make these micro CT scanners. They've given us big educational discounts to have our own scanner. And then Stratasys, which is the 3D printing company whose headquarters here, they've also contributed to the lab and education, and we have 3D printers to do that. So we can actually see, you can see the prints there, but we can print this as many times as we want. And it's really good. We've given away hundreds or thousands of these devices and models to physicians around the world. We also do, like I said, muscle force assessment. We've done these with patients with neuromuscular disorders. And patients will lose muscle after immobilization, and that can be due to surgery or other things. And so we've been studying that, or neurologic disorders. And did that for many, many years. And then out of the blue, one day I got a call saying, how'd you like to study a population of individuals that don't get weak, even though they're immobilized for 4 to 6 months? I said, well, that'd be awesome. Well, it was Hank Harlow, and he said, well, I'm studying hibernating black bears. So I said, this would be great, because I'm from Minnesota. I love the outdoors and everything. So we go to bear dens. And to get the bears, they're radial collared. And what they'll do is they'll do barrel traps. They'll trap them in the center, drug them, and put on these satellite collars. And once they have a satellite collar, you can use Google Maps. You can track them within 10 feet every 15 minutes. So we can look at all these bears. There's about 35 bears in Minnesota that have collars on them. And then basically, I'm working with the Minnesota DNR and collaborators at Medtronic, Tim Lasky, and Dave Garchalis, Andy Try, and we're going to these dens, drugging the animals, and then studying all their physiology. And so the dens can be like on the right here, this movie. You can't even find them. So you actually use a triangulation antenna and you try to find them. That was last winter when we had 4 feet of snow. We had the snowshoe in. Take your snowshoes off, you can't move. We went in December. There was one den with about 1 inch of snow. Most of the other dens didn't have any snow. So they can be sitting out in a nest. Actually, it's harder to drug the animal that's sitting out in the open than when that's down in the den. They seem to be more stable down there. The other thing is that, if they have cubs with them, then they're probably not going to leave the den. So, amazing hibernators. For 4 to 6 months, they don't eat, drink, defecate, or urinate. So you can go about 3 days without drinking water. You can go about 40 days without eating. And these bears are going 4 to 6 months. And they are basically only mildly hypothermic. Their core temperature goes from 37, 38 degrees centigrade down to 35 or 36. They can wake up at any time and defend themselves against predators. And what are the predators in Minnesota? Wolves. Wolves don't hibernate. And this would be a nice, tasty, warm snack for a pack of wolves. But the bear can sense them, and they can arouse from that, wake up, and defend themselves. How do you drug them? Stick your head in there. You've got a jab pole, and this is Dave going in there, and then darting the animal. And they will respond. Sometimes they'll come out at you. Like I said, it's very fun field work.
Through the winter, this black bear drops 60 pounds. It makes for a lighter load as the team transports her for tests.
So here we're measuring the electrical resistance through the bear's body, which we can convert to how much fat the bear has, the percentage fat. The thing is that bears are able to go through the whole winter with just burning almost entirely fat. They don't burn any muscle.
Oh, they're nice and big.
She gives birth to these cubs in January, nurses these cubs, takes care of herself, and the whole time just lives on body fat.
And so actually, if you're keeping track of all that, they actually mate in May, June, July. There's the late implantation of the fertilized egg until late December or November. And then there's a 5-6 week gestation period. They're born in January while the mother's hibernating. And we've monitored all their cardiac activity and motion and everything else. And so we know they're hibernating while they have young cubs in there. So it's really interesting stuff. And the muscle force stuff we did, these bears don't lose any muscle strength during this whole time of hibernation. So we made force devices, went on the top of the mountain in Wyoming and Laramie and Middle Park, Colorado, and studied, measured all the muscle force in early denning and late denning, and really they're not losing anything. And if you were a human, and with full nutrition and everything else, or if you're the Department of Defense and you tell these soldiers to lay in a bed for a month and fully fed and drinking, they're going to lose 0.6 to 0.7% of muscle strength per day. That's why your cardiac rehab nurse wants you up out of bed as soon as possible, so to maintain your strength. And we just heard some great talks on that prior to this. I've done hundreds of echoes on bears and 12 lead EKGs. That's what I loaded in my car before I came. They don't lose any cardiac mass or cardiac function in the state of starvation. And it's phenomenal, right? And so if you're on the space station, how many hours a day do you have to exercise to maintain skeletal mass? How much do they exercise? Anybody have an idea? It's somewhere between 4 to 8 hours a day. So if you're exercising 4 to 8 hours a day, you're burning a ton of calories. It's a food problem if you think you're going to Mars. But there's no electrical or functional remodeling of the heart, which is amazing. So then we implanted data recorders in these animals, and they have a dramatic respiratory sinus arrhythmia. Everybody in this room has a respiratory sinus arrhythmia. Your resting heart rate now is 70 beats per minute. You inhale, it goes up to 71 or 72. You exhale, it goes back down to 70. And it does that all the time. A bear, its heart rate is 5 or 10 beats per minute. It inhales, it goes up to 60 or 70. They exhale, it can stop for 5 to 30 seconds and then starts again in a normal sinus rhythm. And they do that all winter long. If you don't have a heartbeat for 5 seconds, you'll pass out. So it's really amazing physiology. So we were able to put these devices in and track them. This is another example. This is amazing that they can sense what's going on. The upper left there, that's the respiratory sinus arrhythmia. And then we start going to the den. This is before we even given it any drug, they change their physiological behavior. They start huffing, going, which drives up their heart rate, which ready for a fight or flight response. So they're ready to defend. If it's a pack of wolves or if it's a bunch of researchers, they don't know. And so they're ready to go. Then we administer the drug. And this is a whole hypothalamic control center in your brain that does this for the bears. The anesthetic knocks it out, and the heart rate goes to a constant, like 100 beats per minute, like the heart's denervated. And how long does that last? Everybody said, are you disrupting these bears? Are you doing bad things? Turns out that the fact that we have these devices in there, we know that only lasts for 3.5, 4 hours, and they go right back into that pattern they had before, which makes us feel good that we're not really changing hibernation at all. This is one bear that actually we tracked for 6 years, and every other year she gave birth to the cubs, and then the cubs will stay with the mother all the next winter and hibernate with the mother. So one den we went to, there was a 300-pound mom and 3 yearlings, which were 11 months old. They were each 100 pounds. So 600 pounds of bear in a den. And we anesthetized them and studied them all. You can see some kind of funny spikes in between those big waves, and that's the summer activity. Those spikes are us visiting the den. So we can look at motion, we can look at heart rate, and we can really understand what's going on. And so we're changing the technology. We're using Medtronic's latest Link devices on Link 2, which are all Bluetooth enabled. These are cardiac monitors. Some patients might have these. If they have arrhythmias or fainting spells, they'll put that in. It's injectable now, and I've put in 400 or 500 of these in bears. And Tim Lasky, who's pictured there, Tim works at Medtronic, and I think they put him in now 21 different species of animals. He's just got back from Thailand where they put it in elephants, and they're building big collars for them as well. But these bears are doing some amazing physiology. It's been known for a while that bear bile acids can basically be curative for a lot of diseases, but we're actually studying fatty acids, bile acids that are released during hibernation. And then we can take these and then we can use it in the lab. We can do a heart attack model where we can try to induce a heart attack, and we can actually show that if we pre-treat these animals, it reduces the infarct size by 50%, which is very exciting. And so, we'll have these different agents. We'll do a pericardial delivery. So this would be a cradle that you would do for an off-pump procedure, or you would stop the heart and it would be on pump. And you could administer these just in the epicardial space, in the pericardial area there, and you can flush it all out when you're done with the procedure. So we're doing this for a lot of the organ research we're doing in the lab. We're doing this with hearts, the organ care systems for heart transplantation that extends the window of opportunity and transport time. We're seeing if we can even extend that further. So a lot of work we're trying to make all this, what we learned from bears, translational to transplantation and cardiac surgery. And I use it as a research tool in my lab on a weekly basis. So to kind of summarize, our lab really does a lot of translational research, a lot of education. We actually have a QR code cards I'll pass out. We have free apps on cardiac anatomy and echoes. If you want to learn how to do all these, I'll hand those out. The black bears are amazing hibernators, not losing any cardiac or muscle mass, even in a state of starvation, and more or less immobilization. And we really think that this could be translational. And what we're really finding excuses to go back to bear dens and study them, because it's a really cool project and other species. But biomimicry is a big thing. If we can learn from different species how they protect, how they do better wound healing, different things, we hope to bring that back to human medicine. Couple last videos for fun. This is a bear that's been in starvation and hibernating for 4 months. Doesn't look like it's lost any muscle function, right? All right. Sometimes you got to do this in blizzard conditions. We've had 20 below, 30 below wind chills and snowing, and I'm still in planning devices and doing 12 leads and echoes on bears. And I have a lot of hidden talents. Basically, I'm the bear surgeon. If they do have an injury or wound, if it's a gunshot or arrow, I'll try to repair them and help them out. And I actually have long arms, so often I'm pulling bears off the way back of the den, or I'm actually really good at stuffing them back in. So I'm kind of the official bear stuffer when I'm around. And what you do is you get a sled, one of those roll-out sleds, and you lay it down and you slide them back in. And so a lot of really fun things that go with this project. So with that, thank you for your time, and happy to answer any questions during the break. I may not be able to stay all afternoon, but again, thanks for letting me present.